Now screen is okay?
Yes, please, go ahead.
Okay, good. I will read the report. Dear participants of our conference, Zhao Shenhao, in our report, I will give special attention to important feature of LENR, the huge variety of emerging new nuclides. In the experiments of Fleischmann and Pons, which began intensive research in the field of LENR, tritium and helium were formed during the fusion of deuterium nuclei. But very soon it was discovered that cold nuclear transformations are not limited only to the fusion of light nuclides. Within the time allotted for this report, I can only give a few examples of the various nuclear transformations which were found in various numerous experiments. Next slide. Experiments of Savatimova, Karabut, and Kucherov began almost immediately after the publication of Fleischmann and Pons. In these experiments, the effect of a glow discharge in a medium of deuterium and other gases on palladium and other metals was investigated. Release the excess energy and the appearance of many initially absent chemical elements were found, and in some of them unusual ratio of isotopes was found. In addition, gamma and neutron radiation was detected, as well as the appearance of radioactivity of the irradiated targets. However, detected radiation intensity and radioactivity were very weak. Thus, already in these early studies, many import properties of LENR were identified. Irina Samatimova will talk about recent research in this direction in her report later. At the same time, in Magnitogorsk State Technical University, Anatoly Vachayev created installation called Energo-Niva. In this installation, water flowed between tubular electrodes, between which a special tube of electric discharge was created. As a result, many elements that were initially absent appeared in this water, from lithium to lead. Most of all, iron appeared. In addition, heavy and super heavy water accumulated in the water, so deuterium and tritium appeared. Vachayev installation was reproduced in several laboratories. The appearance of many initially absent nuclides occurred everywhere. Appearance of many initially absent nuclides was also recorded in the well-known experiments of Leonid Urutskoev with exploding metal foils. A change in the isotopic composition of titanium after an electron explosion was detected. In the experiments of Ubaldo Mastromateo and Jean-Paul Biberium, palladium foils were subjected to prolonged laser irradiation in atmosphere of hydrogen and deuterium. In the field of irradiation, appearance of many new chemical elements and a significant decrease in the content of palladium were detected. In our laboratory, various substances were exposed of incandescent lamps. The release of excess heat and change in the element's composition in the substances surrounding the lamp were detected. One of these devices is shown on the slide. The tube-shaped incandescent lamp was wrapped in a lead-thin alloy ribbon. In order to prevent the alloy from melting, leaking water was used. The next slide shows the results of the analysis of chemical elements before and after being in working reactor. Appearance of many elements ranging from lithium to bismuth has been reliably detected. It is important to note the following. Many attempts to explain LENR include hydrogen or deuterium as a necessary element of the process. In the lead-tin experiment, nuclear transformations occur in the complete absence of hydrogen. This indicates the need of approach to explain LENR that do not require the mandatory presence of hydrogen. Many nickel-hydrogen reactors have been tested in our laboratory. In some of them, elemental and isotopic composition of both the nickel-hydrogen core and the surrounding matter is analyzed. Appearance of many initially absent elements has always been detected, but not only in the core, but also in the surrounding matter. This slide shows one of the reactors that has been running continuously for 7 months, generation up to 1000 watts of excess power. Following slide shows that new elements have appeared in different parts of the reactor after the end of its operation. New elements appear in all parts of the reactor located near the core, even in outer ceramic tube. Analysis was made of the isotopic composition of nickel, which, along with hydrogen, was considered as fuel. Contrary to expectations, after a long stay in a working reactor, it almost did not change. The isotopic composition of nickel remained almost unchanged in our other nickel-hydrogen reactors. This indicates that LENR process, heat generation, transmutation, occur not so much in hot nickel-hydrogen core, but in surrounding matter. Numerous various experiments allow us to identify a number of important features of LENR. Huge variety of nuclides appears not only in the field, but also in surrounding matter, and in general, nuclides that do not have radioactivity appear. Energy is realized in far beyond the capabilities of chemical reactions. Neutrons and gamma radiation are emitted during the LENR process. However, the radiation intensity is many orders of magnitude lower than in normal nuclear reactions. Sufficiently dense medium, solid, liquid, dense plasma is required. Unusual tracks appear near the reactors. Many attempts have been made to explain the LENR phenomenon, but so far it has not been possible to explain all the features of LENR, or at least some of them, without contradicting the rest. Basically, the search went in the direction of finding ways to overcome the Coulomb barrier, which prevents a sufficiently close approach of the nuclei. An example of the approach is well-known Weidenlawson theory, which allows possibility of converting protons into neutrons. Resulting neutrons react with the nuclei in the surrounding matter, forming new chemical elements. However, in reality, experiments did not detect the intense radiation of neutrons and hard gamma rays, which inevitably occur when neutrons are captured by nuclei. This alone refutes the type of hypothesis. Similar inconsistencies are typical for other approaches. I would like to notice that none of the above approach provides an explanation for the huge variety of nuclides that arise. The problem of the appearance of huge variety of emerging nuclides can be solved by the assumption that they appear as a result of energy efficient rearrangements of nucleus located in 2 or more atoms. To do this, they must be exposed to action that covers several atoms at the same time. As far as I know, the idea was first brought forward by Leonid Urutskoev and Dmitry Filippov. The assumption of the multi-core nature of the transformations indeed indicates the possibility of appearance of numerous diverse nuclides. This slide shows, as example, possible transformations in corundum, substance that has been widely used in our reactors. Even when considering the interactions of only 2 aluminum nuclei, many new helium, 2 iron nuclides can arise. Additional nuclides can arise from interactions of 2 oxygen nuclei and nuclei of oxygen and aluminum. It should be noted that such transformations cannot occur through the channel of strong interactions due to Coulomb barrier. But nothing prevents, in principle, such transformation to occur through the channel of weak nuclear interactions. As I have already mentioned, for the implementation of multi-core interactions, a mechanism covering several atoms is necessary. This slide shows several possible mechanisms. Due to the time limit, I will only consider the last one listed, ultra-low energy neutrinos. Be careful, long slide. At present, there are no exact data on rest mass of the electronic neutrino. Direct experiments indicate that it is less than 2 electron volts. Estimated based on astronomical observation give a mass value of less than 0.28 electron volts. If it is true that the mass of the electronic neutrino and antineutrino is so small, then they can be formed as a result of inelastic collisions of matter particles, electrons, ions, neutral atoms, during their thermal motion. The energy of the colliding particles should be on the order of 0.5 electron volts or higher. At room temperature, there are very few particles with this energy. But at a temperature of 2000 Kelvin, there are already 10%, and at 5000 Kelvin, half. Especially often, electrons collide with atoms in metals. In 1 cubic centimeter, there are about 10 of the power of 36 collisions per second. Such a high frequency of collisions lead to the appearance of huge number of neutrinos and antineutrinos, even with a very small probability of their formation. The resulting neutrinos and antineutrinos can be interact with the nuclei of the surrounding matter. In addition, neutrinos and antineutrinos can appear from light photons since their energy is sufficient to form a pair of neutrinos-antineutrinos. It is important to note that de Broglie wavelength of imagined particles is about 1 micron. This means the region of interaction covers a huge number of atoms, which makes possible transformations involving many atoms and nuclei, as a result of which even unlikely processes become significant. The next slide shows dependence of de Broglie wavelengths, that is, size of the interaction region, on the neutrino energy. It can be seen that at energies of the order of 10 kiloelectron volts and higher, only one nucleus can be covered by the interaction. At energies of several thousand electron volts, the interaction covers several atoms. And neutrinos, which arise from thermal collisions of atom of matter with an energy of less than 1 electron volt, cover many billions of atoms by their interaction. The following slide shows some examples of possible nuclear transformation of 2 nuclei, electron and neutrino or antineutrino. In nickel, and in nickel with participant of hydrogen, iron, cobalt, copper, and helium can appear. Appearance of iron from water in the energon reactor becomes clear. Combination of the nucleus contained in 3 water molecules and 4 electrons gives the iron nucleus. Finally, it is possible to explain paradoxical phenomenon discovered by Louis Kervran. In the absence of calcium in feed, Hahn managed to produce calcium from potassium. This transformation cannot occur through strong interaction channel due to Coulomb barrier. And if it could, huge realize of energy in the nuclear reaction would burn the Hahn. However, in the same transformation goes through the channel of weak interactions involving neutrinos, both of those problems are solved. Triggering this transformation, neutrinos with an energy of less than 1 electron volt can be generated during cellular metabolism. As a result of the nuclear reaction, two particles arise, calcium nucleus and neutrino. Since in a system of two particles, the energy is distributed inversely to the masses, almost all energy is carried away by neutrino without leaving it in the hand. Thus, unlike many other hypotheses of neutrinos participation in nuclear transformations allows us to explain many features of LENR. Appearance of a large variety of nuclides not only in fuel, but also in surrounding matter. Need to heat or give matter particles energy of order of 1 electron volt in another way. Need for a sufficiently dense environment. No or very low intensity of hard nuclear radiation. In nuclear transformation involving neutrinos, there is no Columbian barrier problem. Thank you for your attention in our report, Woman, Han, Gaussian, Zhenshi, Nin, Men.
Well, thank you. Thank you very much. There's time for quite a few questions. Who would like to be first? Evgeny. You need to unmute. There you go.
Are you listening to me? Are you listening?
Yes, yes, we can hear you.
Thank you. The question, what can you talk about microleptons in new transmutation reaction? Microleptons was found Akhatrin, Tatur, Savelyev, and other authors. This is quasi-massive particles, but they has a magnetic field. По-русски я могу. Значит, Саш, что вы думаете об участии микролептонов в ваших реакциях? Микролептоны — это такие частицы, да, которые Акhaтрин, Татур, Савельев и другие описали, открыли и даже используете. Спасибо.
Alexander, you are muted. Could you unmute yourself, please?
Микрофончик включить надо.
Yeah, I can't do it from here. Could you ask your grandfather to click on the mute button at the bottom left corner?
I clicked.
О, вот. Слышно теперь, да?
Да.
Я был знаком с Анатолием Акхатриным, бывал в лаборатории, даже пытался некоторые эксперименты сделать в соответствии с его идеями. В свое время это была очень популярная, значит, точка зрения, что многие понятные эффекты происходят благодаря действию так называемых микролептонов. Но сам Анатолий, значит, Акхатрин говорил, что, возможно, это некая разновидность нейтрино.
Alexander was familiar with Akhatrin and worked with him together. They tried to make experiments due to the theory of Akhatrin and tried to find microneutrino. But even Akhatrin thought that it is possibility that microneutrino is a type of neutrino.
Okay.
Luciano.
Please, thank you for your excellent presentation. So for me, it's a little bit even shocking because it was far from what I was expecting. So very good. So, well, you presented that there aluminum as a source of reactions. Did you find a reduction in the aluminum quantities in the comparing with the original quantities in the reactor materials?
Recording in progress.
Your ask is if you find the rise of aluminum, right?
What happened?
Something happened.
You're good now, Alexander. You speak.
If the question, if he found excess of aluminum or not, ну, спрашивают, ну, похвалили за хороший доклад, презентацию, работу, но и спрашивают, находил ли ты увеличение количества алюминия относительно изначального?
Но дело в том, что после разрушения, после того, как для того, чтобы сделать анализ, надо разрушить реактор. И после этого трудно установить изначальное количество элементов. Можно установить только, было что-то или нет, и появилось ли что-то или нет. Поэтому сравнение с тем, чего было очень много, это затруднительно.
To make analysis, we need to destroy the reactor, and it's difficult to say in which part of reactor which elements was in low concentration or in high concentration. So we haven't problems with elements with a huge excess, but it is difficult to say from what part of reactor came aluminium and if it is extremely or not.
Raj?
Yeah, thank you for the interesting talk. So in one of the slides, you mentioned that the reason can be atom forms a more compact atom and then releases heat, right? So can you please clarify or elaborate on that statement?
I don't understand you. One more time, please.
Like in one of your slides, probably slide 12 or something, like a few more, you mentioned the reason for LENR. You gave some 4 reasons. And one of the reason was the atom forms a more compact atom and it releases heat or releases energy, which can initiate LENR. So you had mentioned something like that in the slide.
In which slide?
Maybe if you, maybe 12, if you can just scroll through the slide, I can show you.
Можешь назад переключить, где у тебя тезисы были, несколько слайдов полистать?
So as I understand the question, something initiates the heat production. There's a spark and then a fire.
Yeah, so in this slide, the slide 11. Slide 11. Slide 11.
Next one.
Следующий. 11 слайд.
The next slide.
Yeah.
Yeah, so here. So atom goes into a compact state with the release of high energy. What exactly do you mean by that?
Вот пояснить последний пункт просят.
Но есть несколько теорий, в которых значит, предполагается, что электроны на атомной орбите могут находиться не только вот в обычных состояниях, но и на орбитах значительно более низкого радиуса. И при переходе на эти орбиты происходит большое выделение энергии. И кроме того, значит, вот эти компактные получающиеся атомы, они уже значительно легче преодолевают Колумбовский барьер.
There is some theories due to there are no only atoms with electrons on normal orbit, but there are some atoms with electrons on lower orbit, with orbits with lower radius. And for these atoms, which are more compact, it's likely to override the Coulomb barrier.
Yeah, we could have time for one more question. Jacques, 1 minute question and a 1 minute answer.
Thank you very much. I would like, please, to go back to slide number 6. Slide number 6, please. This is, I am impressed by your presentation. And for example, this slide number 6, 2 times 3. This is a slide relating to this experiment with this incandescent lamp. Slide number 6, please.
На 6-й слайд переключись, пожалуйста.
And I have a simple question. In this experiment, okay, this one, thank you very much. How did you measure the electrical consumption? To be more precise, did you measure at the same time the voltage in volts to this incandescent lamp, but also the current in amperes to this lamp? How did you measure this electrical power consumption, 480 watts, please?
Yeah. Okay.
So how was the 480 watts measured? What was the measurement system?
Yes,
Каким
exactly.
образом ты измерил 480 ватт?
Ну, обычным способом, используя вольтметр и амперметр.
By voltmeter and ampermeter.
Okay, okay.
I have
Sorry? Well,
могу добавить, что избыточная энергия определялась по скорости роста температуры воды. То есть суммарная энергия определялась по скорости роста температуры воды, и вычитая потребляемую энергию, можно получить, значит, избыточную энергию.
He added that he measured the excess power due to the rising of temperature of water.
thank you. But my question was about the electrical power.
Electrical input, yeah.
480 watts input. How was this 480 watt input measured?
А как ты входящие 480 ватт измерил?
Обычным способом, используя вольтметр и амперметр.
Simple voltmeter and ampermeter.
Okay, thank you very much.
I think we're good. I will thank you very much, Alexander. It was an excellent presentation, and we'll move on to the next talk. Thank you.
Okay. Можно чего-нибудь посмотреть. Видишь, сколько качества сидит.